Ever pondered how multiple processes or threads manage access to shared resources in concurrent programming? The answer lies in a fundamental synchronization primitive called semaphores. Imagine a bustling city, teeming with traffic. Picture intersections where roads converge, and drivers need to navigate their vehicles without colliding with each other. Now replace these cars with threads and processes, and the intersections with shared resources. Just as traffic lights control the flow of cars, semaphores control the flow of threads and processes, ensuring they don't crash into each other while accessing shared resources. Semaphores were first introduced by the Dutch computer scientist Edgar Dijkstra in the year 1965. He devised this concept as a solution to problems arising from the concurrent execution of programs. Semaphores are like the unsung heroes of concurrent programming, working behind the scenes to prevent chaos and maintain harmony among threads and processes. At its core, a semaphore is a variable that helps us to control access, prevent race conditions, and enable mutual exclusion. A race condition, in the simplest terms, is a situation where the outcome depends on the sequence or timing of uncontrollable events. It's like a relay race, where the baton passing must happen in a certain order for the race to proceed smoothly. If not, there could be chaos. Similarly, mutual exclusion is a principle where only one process or thread can execute a critical section of code at any given time. Think of it as a narrow bridge, where only one car can pass at a time. Any more than that, and there could be a crash. Lastly, semaphores allow for coordination between threads or processes. This means that a process can signal another process to start or stop execution based on certain conditions. It's like a relay race again, where one runner signals the next one to start running. So semaphores play a crucial role in concurrent programming, helping us to navigate the complexities of managing shared resources. They act as traffic controllers, ensuring that everything runs smoothly and efficiently. Let's delve deeper and explore the two main types of semaphores. Firstly, we have binary semaphores, which operate much like a light switch, with only two possible states. Imagine you're in a room with only one doorway. This doorway can either let you in or out, but never both at the same time. This is essentially how binary semaphores function. They are the simplest type of semaphore and are used to control access to a single shared resource. At the heart of binary semaphores is the ability to take only two values, 0 and 1. These two values represent the semaphore's state and determine whether a thread or process can access the critical section or shared resource. When a binary semaphore is set to 1, it signifies that the shared resource is available for use. In turn, a thread or process can acquire the semaphore and proceed to execute the critical section. On the other hand, when the binary semaphore is set to 0, it indicates that the shared resource is currently in use. Consequently, any other thread or process that attempts to acquire the semaphore will be blocked until the semaphore is released and set back to 1. Binary semaphores play a crucial role in ensuring mutual exclusion. Just as only one person can pass through the doorway at a time, only one thread or process can acquire the binary semaphore and access the shared resource at any given time. This mutual exclusion allows for orderly access to shared resources and prevents race conditions where multiple threads or processes attempt to access the same resource simultaneously. So, in essence, binary semaphores are like guardians of shared resources. They allow orderly access, prevent chaos, and ensure that each thread or process gets its fair turn to use the shared resource. Binary semaphores may seem simple, but their ability to manage access to shared resources is fundamental to concurrent programming. Despite their simplicity, they play a critical role in maintaining the harmony and efficiency of multi-threaded and multi-process systems. Now let's move on to the second type of semaphore, which is a bit more complex. Secondly, we have counting semaphores, which, unlike binary ones, allow more flexibility and control. Counting semaphores are an interesting breed that offer a more nuanced approach to managing access to shared resources. Where binary semaphores are like a single key to a single lock, counting semaphores are like a basket of keys, each one giving access to a different instance of a resource. They can take on any integer value, which is primarily used to represent the number of free resources available at any given time. Imagine you have a pool of resources, perhaps a fleet of delivery trucks or a cluster of servers. You want to ensure that no more than a certain number of these resources are used at once. This is where counting semaphores come into play. You initialize the semaphore with the total number of resources you have available. This is your starting point. Each time a process or thread wants to use a resource, it must first acquire the semaphore. This is like taking a key from the basket. The semaphore's value is then decremented or reduced by 1, reflecting the fact that one of your resources is now in use. If the value of the semaphore is 0, this means all resources are currently in use, and any new process or thread that wants a resource must wait. It's as if all the keys have been taken from the basket, and you must wait for one to be returned before you can proceed. When a resource is no longer needed, the process or thread releases it, incrementing the semaphore's value by 1. This is like returning a key to the basket, ready for the next person to use. In this way, counting semaphores provide a dynamic method of controlling access to a pool of resources. They ensure that resources are used efficiently without overloading the system, and that waiting times are minimized. Now that we've covered the types of semaphores, let's examine how they work. Semaphores operate through 2 main actions: the wait and signal operations. These operations serve as the very core of semaphore functionality, and understanding them is crucial to harnessing the power of semaphores in concurrent programming. Let's start with the wait operation, also known as the acquire operation. When a process or thread needs to enter a critical section or access a resource, it performs the wait operation on the corresponding semaphore. This operation checks the semaphore's value. If that value is greater than 0, the semaphore is decremented, and the process proceeds. It's like getting a green light to go ahead. But if the semaphore's value is 0, the process is blocked. It must wait until the semaphore is positive, indicating that the resource is available. It's like waiting at a red traffic light until it turns green. Now, let's move on to the signal operation, also known as the release operation. This operation comes into play when a process or thread is done with a critical section or wants to release a resource. It performs the signal operation on the semaphore, which increments the semaphore's value. If there are any processes blocked waiting for this semaphore, one of them gets unblocked and can proceed. This operation is like giving the green light to another waiting process, saying, "I'm done, now it's your turn." These operations, wait and signal, form the heartbeat of semaphores, dictating the rhythm of resource allocation and release. They ensure that processes and threads get their fair chance at accessing shared resources, while keeping the system in harmony. However, it's important to note that semaphore operations are not immune to challenges. They require careful handling to avoid common pitfalls such as deadlocks, where 2 or more processes end up waiting indefinitely for resources held by each other. Proper implementation and debugging are crucial when using semaphores to ensure that they are used correctly and efficiently. With a good grasp of semaphore operations, let's explore some practical applications. Semaphores are like the unsung heroes of systems programming, silently managing a variety of scenarios. They're the invisible conductors orchestrating the symphony of threads and processes that make our software sing. Let's dive into some of these practical applications. First up, resource management. Imagine you're running a luxury hotel with a limited number of rooms. A semaphore, initialized to the total number of rooms, can ensure that no more guests check in than there are rooms available. Each time a guest checks in, the semaphore is decremented. When a room is vacated, the semaphore is incremented. Simple, right? Next, let's consider producer-consumer problems. Picture a conveyor belt in a factory. On one end, you have the producer, churning out widgets at a steady pace. On the other end, the consumer, packing these widgets for shipment. A semaphore can be used to keep track of the number of widgets produced but not yet packed. If the belt is empty, the consumer waits. As soon as a widget is produced, the consumer springs into action. Finally, we have reader-writer locks. Let's think of a popular online encyclopedia that anyone can edit. Many readers can access an article simultaneously, but when a writer steps in, they need exclusive access. With semaphores, we can manage this delicate dance. A binary semaphore can ensure that either multiple readers can access the data, or a single writer can, but never both at the same time. These are just a few of the countless scenarios where semaphores come to the rescue, making the complex task of synchronization manageable. However, remember, with great power comes great responsibility. Semaphores require careful handling to avoid common pitfalls like deadlocks, where processes end up waiting indefinitely for each other. And that's how semaphores make the complex world of concurrent programming manageable. Remember, though powerful, they require careful handling to avoid pitfalls like deadlocks. So, happy coding! And until next time, keep exploring the fascinating world of programming.